Overcurrent protection is often the first line of defense protecting networks against faults. In this video, we're going to look at the basic principles of overcurrent protection. And our starting point has to be the electromechanical relay, because much of the terminology required to understand and operate modern digital relays has a physical meaning which can only be understood this way. The fundamental principle of overcurrent protection is to continuously monitor the current on the system, and if it seems too high, it will disconnect the feeder. The measurement of the current is done by the current transformer. This steps down the current to a low enough level to be measured properly. Now, the device which takes the current and decides if the feeder should be disconnected is called the relay. This is the brains of the system. And of course, the circuit breaker has the physical ability, if instructed, to break fault current and disconnect the faulty part of the system. Also shown here are the disconnectors and the power transformers, but they're not critical to the protection system that we're going to talk about today. The current transformer, or CT, has the ability to step down the current on the line to a proportionately lower level. This is absolutely necessary because the fault current is way too high to measure directly. Now, the CT is very much like a standard transformer, where the line current is the primary, and we can construct a secondary with the number of turns we require to step down the current. Now, in the electromechanical relays, this secondary CT current is actually fed straight into the relay and has a direct effect on its operation. More on that a bit later. But as you can see here, we know the line current because we know the CT ratio. So in this case, if 100 amps is flowing, we know that there's going to be 5 amps on the CT secondary. Inside the relay, let's take a look at what happens when we have a 200 amp line current and a 10 amp relay secondary current. The current through the relay has generated a magnetic field which induces a torque in an induction disc. The induction disc therefore rotates, and if it rotates far enough, a rotating arm hits a contact, and this initiates the instruction to the circuit breaker. Now, we don't want the breaker to operate under normal conditions, so there's a threshold beyond which the relay will operate. And the higher the fault current, the higher the relay current, and the stronger the deflecting force on the induction disc will be. So the relay will operate faster for higher fault currents. We also note that the operating time depends on the distance the rotating arm needs to travel. And we also note that the sensitivity of the relay to current can actually be changed. These final 2 points are really important because they allow us to configure the relay to suit a particular set of requirements, as we'll see. Let's plot the operating time of the relay as a function of relay current. As expected, at high current, the relay operates very fast, but as the current drops, the operating time becomes longer. And it's important to recognize 2 features of this curve. Firstly, we have a minimum operating time. No matter how high the current gets, the operating time will not drop below this. Second, we have what's known as the pickup current. This is the minimum current at which the relay will start operating, albeit very slowly. Now, I mentioned before that there are 2 ways to configure the relay. The first one I'll talk about is called the plug setting. This allows the user to change how sensitive the relay is to current. And quite simply, the position of the plug determines how many turns couple into the magnetic core, which helps to induce torque into the disc. The higher the plug setting, the less sensitive the relay is to current. In fact, the pickup current, that's the current necessary to make the disc move, is proportionate to the plug setting. So if a plug setting is 100%, that's equivalent to a 5 amp current setting. 200% would mean a 10 amp current setting. So twice as much current would be needed to move the disc. Conversely, a 50% plug setting requires only 2.5 amps to move the disc. But instead of having a graph to show each plug setting separately, we can normalize to the current setting, and this means you only need a single graph to show all possible plug settings. The x-axis is now called the plug setting multiplier, and this is a more universal way to show a particular relay characteristic. The second method to configure the relay is called the time multiplier. This allows the user to change the distance that the rotating arm needs to travel to reach the contact. The ability to do this is a remarkably useful way to set a relay to a particular requirement. For example, the time multiplier setting is a crucial parameter for coordinating the speed at which relays operate. In some cases, multiple relays are spread along the feeder, and in order to ensure that only the faulty part of the network is disconnected, each relay can be carefully set such to guarantee that the relay directly upstream from the fault is operated, thereby ensuring that all customers in the healthy part of the network can remain on supply. This process is called discrimination. I hope you enjoyed this introduction to overcurrent protection. See you in the next one.